Armstrong. I am the Executive Director of Illinois NREC, and first want to thank Illinois Farm Bureau for partnering with us and for their help with getting this webinar pulled together. From the attendee list, it looks like some of you were able to join us earlier in the year where we did a phosphorus webinar. If you weren't able to participate in that, that is housed on our website, which is illinoisnrec.org, and as Lauren mentioned, this cover crop webinar will also be archived and put out on the website. So if you missed something and want to go back or want to share it with other folks in your organization or your farm operation, you'll have access to that as well. So we're going to go ahead and dive in and start going through some of the information. Just a quick background about who NREC is and what we do. So NREC was created in 2012, and it was created through state statute. So it went through the legislature to become an organization that is focused on pursuing nutrient research and educational programs. And our main goal is to ensure that adoption and implementation of practices that optimize nutrient use efficiency, ensure soil fertility, and address environmental concerns with regard to fertilizer. All of the activities that are done by NREC are funded by an assessment on fertilizer that's sold in Illinois. That's 75 cents per ton. So that's paid by farmers, but then collected through retailers across the state. And NREC is a collaboration between ag, environmental groups, and state agencies. Primarily, we are focused on, as I said before, the issues around nutrient efficiency, which can lead to enhanced crop production and then also protect our water quality. So we've worked very closely with a lot of different agencies and organizations across the state, focused primarily on the nutrient loss reduction strategy, and I know that Dr. Armstrong is going to touch on a couple of those issues. But each year we solicit proposals that focus on those issues, and then the council, our research committee, and independent peer reviewers review the applications, and then we rank projects based on merit and availability of funds. We primarily look at three main areas. The first is really being as efficient as we can with nutrients on the front end. So that's looking at the 4 R's, which is right source, right rate, right timing, and right place. And there's a lot of research and a lot of information out there. And again, that's kind of the first step of making sure that we're as efficient as we can be. The next thing is looking at recovering in field. So knowing we can't and we probably won't get 100% efficiency through the 4 R's, we want to make sure that we can recover as much of those nutrients in field. And that's primarily where the research around cover crops comes in. And again, that's really going to be the focus of what we're going to talk about today. And then the next part is recovering and reducing. So where we can't gain 100% efficiency through those first 2, we want to make sure that we can manage any escaping products in a way that can minimize environmental impact. So that's things like bioreactors, buffers, wetlands, those types of things. In 2016, we have 26 projects that are going. 17 of those are ongoing, and again, Dr. Armstrong's projects are in that ongoing group. And we do have 9 new projects we're looking at. We work with a variety of folks, including University of Illinois, Southern Illinois University, Illinois State, the Wetlands Institute, and then 2 county soil and water conservation districts. And this year, there's $2.8 million that have been awarded and going towards these research projects. And we're at approximately $9.3 million that has been awarded over the past 4 years. So with that, I'm going to get ready to hand it over to Dr. Shalamar Armstrong. And we always have to tell people when we're on a program together, no relation. But Dr. Armstrong is the Assistant Professor of Soil Conservation and Management in the Department of Agronomy at Purdue University. But a lot of the research that he's doing through the NREC funding is through a partnership with Illinois State University. And most of the research is being done here actually in McLean County and in the Lake Bloomington Watershed. So we're going to start off, and he's going to go over field scale looks at cover crops and nitrogen efficiency within those. But then he also is going to go over some watershed level results as well. So again, thank you for joining us, and we will take questions at the end or if anything comes up as we go through.
Okay, thank you, Lauren and Julie, for the introduction and this wonderful opportunity. Just to share a bit some highlights about what we've found in my research program over the last 5 years. I would like to acknowledge Dr. Catherine O'Reilly, who is not here today, and her work as a collaborator on all of the projects that you will see in a few minutes. So most of you understand that the state of Illinois and other Midwestern Corn Belt states have had to develop a nutrient loss reduction strategy. In this state, we have a target to reduce total phosphorus and nitrate and nitrogen that reaches Illinois waters by 45%, 25% reduction for phosphorus, and then 15% reduction for nitrogen by 2025. Now, it's really important. My philosophy is that in order to achieve this target, to reach this target, we have to think about all of the nutrient management practices, and we have to think about them on multiple scales. So, for example, a lot of work has been conducted, research has been conducted on spring-applied nitrogen management systems. However, if you are from Central Illinois, you would understand that not all of the nitrogen is applied in the spring. There's quite a bit of nitrogen applied in the fall. In fact, just looking at the local recent surveys, you'll find that about 50% of the nitrogen of farmers apply nitrogen in the fall. That's in Central Illinois. And then if you think about regionally, Illinois is not by itself with that type of trend. Regionally, a USDA report came out that says that 41% of the nitrogen of the land that is treated by nitrogen is treated in the fall, and that's in the Corn Belt states such as Iowa, Missouri, Illinois, Indiana, and Ohio. So with that said, and with that premise, in 2011, I began to think about what's the impact of cover crops on fall applied nitrogen, and we developed this management practice. We call it a green nitrogen application. And the premise of this is that you have a living cover crop stand, and you come back when the soil temperature is correct, below 50 degrees, and you inject your anhydrous into this living stand. This stand of nitrogen, we hypothesized that it would interact with this stand of cover crops would interact with the anhydrous after being applied and stabilize it and assimilate it into its structure, keeping it in the organic form, not allowing it to denitrify and not allowing it to leach and then be intersected by tile and then reach surface waters. And what we found is that depending on the type of weather we have that winter, the interaction of cover crops with that nitrogen may change. And so over the last 5 years, I've selected 3 years that have 3 different types of weather patterns. So when you think about a normal winter when the ground actually freezes, so the winter between 2014 and 15, you can see this graph where we have on the vertical axis the soil depth, and where those 2 zeros are at the top left-hand corner. You can think about that horizontal axis as the soil surface. And so you would have soil nitrate increasing as you go away from the zeros, and then your depth is increasing as you move down from 0 to 90. And so we took soil samples after fall applying into a living stand of cover crops in the spring to see what was there and if the plume of nitrogen had moved from its original injection point. And so we sampled down to 2.5 feet. And in this field at the Illinois State Research and Teaching Farm, the tile drainage was about 3 feet. So we were thinking that if the nitrogen gets down to 2.5 feet, then by the time early seedlings can get their roots to that point, that nitrogen has been eliminated from the system, and they couldn't use it. So we fall applied into cereal rye, radish alone, daikon radish, and then the mixture of cereal radish. And what we saw, and when the ground freezes, you don't have much difference in the formation of this graph, or the shape of this graph, where you see the peak of the nitrogen is right where we injected it at about 20 centimeters deep below the soil surface. So when you think about a wet spring, okay, coming after, following the drought of 12, so that's the winter of 2013, 2014, you see the shape of that graph totally changes, where you see most of the plots, or most of the treatments are increasing in nitrogen as you increase depth. So this is, indicative of we had a wet spring. As it warms up, the ammonium goes to nitrate, and then that nitrate begins to move through the soil matrix and down to the lower portions of the soil profile. But where you had nitrogen applied into a living stand of cereal, you had less nitrogen in the system total. And so you have less movement and less nitrogen, significantly less nitrogen at the lower depth at 2.5 feet. Where you had anhydrous injected into radish, you have more, and radish and cereal, you have more of that nitrogen at closer to the surface compared to the nitrogen moving down to the lower portions of the profile closer to tile drainage. And so that's a winter where you had a drought, you had significant concentrations of residual nitrogen there, and then followed by a wet spring, you get movement of that nitrogen, but less movement when you have a cover crop present. So worst case scenario. Worst case scenario for this situation where you're all applying nitrogen is to have a warm, wet winter, okay? And even with NSERV or some type of inhibitor present, the conditions, the environment are such where nitrification is rampant. And so what we found in this particular situation was that the plume of nitrogen where there's no cover crop did move down to the lower depth and was significantly greater in concentration, closer to where the tile was compared to where you fall applied into the 3 different cover crops. And so, again, you see cereal basically robbing the soil of any inorganic nitrogen. That's why it's closer to, the concentration is closer to 0. And then you see the cereal radish mix and radish alone behaving very similarly, where there was more nitrogen in the profile compared to cereal and less nitrogen at the lower depths relative to the control. So those are the 3 different scenarios that you can get. You can have a wet spring, you can have a warm and wet winter, which is the worst case scenario, and then you can have where the ground freezes and what we were used to, and the nitrogen basically is stabilized there, the microbial activity is really low, and so you don't get nitrification, so you don't get the formation of nitrate, and you don't get that movement, and so your nitrogen is where you put it in the spring, okay? So we wanted to see if what we found on a field scale, on a plot scale, could transfer to a field scale, especially when we add tile drainage. And so that's the premise by which we developed our field scale study, where we wanted to look at the effects of cover crops and nitrogen application timing on nutrient loading through subsurface drainage. And Dr. O'Reilly worked on this project with me, along with 2 wonderful graduate students who really allowed me to be sitting here today. That's Richard Roth and Michael Rafati, and also Travis Deppy and Corey Lacey. So let's just dive in. So the objectives of this study were to determine the impact of nitrogen application timing on nitrate losses via tile drainage, to evaluate the influence of nitrogen application timing coupled with cover crops on nitrate loss, to quantify corn in uptake and crop yield. So it's not enough just to say to a farmer, hey, cover crops are going to reduce your nitrate loss. They want to know, most of them want to know what happens, how does the cover crop impact the nitrogen nutrition of the plant, and then how does that affect yield, okay? And so, and our last is we wanted to effectively educate farmers, and that's what we're doing today. So let's put this in the context of the nutrient loss reduction strategy. So the strategies that we're evaluating is, number one, moving that nitrogen from the fall to the spring. Number two, we wanted to determine if what would happen if we add cover crops to a fall system and add cover crops to a spring system. Would there be any difference in yield? Would there be any difference in corn uptake, nitrogen uptake? Would there be any difference in what's lost through the tile? Third, and so that takes care of our third bullet, where we wanted to add cover crops to a fall applied system. We did this through strip till. So basically, we established the cover crop, and then we came back and strip till, and then that strip till pass, the anhydrous was injected into a living stand of cover crops. So treatments. I know there's a lot on this slide, but bear with me. I'm just going to walk you through it. We have a zero control, and you'll hear that term throughout this particular study. The zero control is very unique. There's no nitrogen fertilizer added, and then there's no cover crop added to that system. So this system is basically in a natural state, except that we allow the crops to grow in the system, okay? We wanted to have this there so that we can kind of get an idea of what the soil gives without any nitrogen being added, okay? And so the next two, treatments 2 and 3, are what we call our spring split application of nitrogen, where it's dominated by an early spring, pre-plant anhydrous application, but we did have 20% of that nitrogen applied in the fall in the form of diammonium phosphate, DAP, okay? Treatments 4 and 5 are your fall-dominated systems, where 70% was applied in the fall in the form of anhydrous and DAP, and then 30% applied pre-plant with anhydrous, okay? And both of those are with and without cover crops. And so total rate of nitrogen applied was about 200 pounds per acre, and the cover crop that we used was a cereal radish mix. Why that particular mix? Well, we found over our studies on a plot scale that mix best meets the agronomic and environmental needs. Why? The radish, the daikon radish, grows rapidly and vigorously in the fall, and its uptake is also very fast in the fall. However, it winter kills. And so when you get temperatures in the teens for over 3 or 4 days, you'll see it begin to turn yellow, and it'll begin to desiccate, and it'll winter terminate. Now, the cereal rye grows slowly and uptake nitrogen slowly in the fall if you have a normal winter. And then it kind of lays dormant and then comes back and grows vigorously in the spring. And what we like to think is that there's a nitrogen relay from the radish to the cereal rye, and then you get further uptake of nitrogen. And so one question is, what pools of nitrogen are the cover crops actually interacting with? Well, there are 3 pools. There's the naturally mineralized pool of nitrogen. There's residual nitrogen from the previous season, if you're in a corn-on-corn system, and even if you're in corn-soy system. And then there's the nitrogen that's applied during the early establishment of the cover crop in the fall. So there are 3 pools that this cover crop could actually interact with. We don't know exactly what percentages at this point, but we are going there in our research program. So let's just talk about the setup real quick, and then we'll get to some data. So this was, I was able to join and collaborate with a farmer that was already pretty innovative. When I got there, they were already in 8 years of strip till before corn, no-till before beans. And so I don't tell farmers what to do. I'm just a visitor on that farm, and so he was adamant about strip till and the benefits of warm up in the, being warm and dry in the spring so he can get in early in a high residue system. And so he convinced me, and we went forward with that. His nitrogen management practice before he met me was about 60% fall and 40% spring, so he already had 2 applications, which is pretty good. And not having it all in the fall or not having it all in the spring, he thought that fit his system the best. And so he allowed me to come in and to pattern tile very extensively. And so what we have are 15 individually tiled fields that are about 1.6 acres, 72 rows wide. Each field, you can see those red lines, have 3 laterals that converge about 15 feet from a control structure, and that's where we tap into the tile water and then collect it to take it back to the lab and measure. So the tile monitoring station, they are those yellow squares that you see. And so each one of those treatments that I mentioned are replicated 3 times. And so each data point that you see is an average of 3 different measures. And so that way we can be very robust with our data when we do see a trend. So this is what the tile monitoring system consists of. I think most people know controlled drainage structure. And then so we have within that controlled drainage structure a device that measures flow, a device that measures the temperature of the water and the head of the water, the water table height, okay? And so within that white box that's solar powered, we have a communication and data storage system, and we have an automated water sampling system. That saves my graduate students from running out there every time it rains. It sends a text to their phone and then allows them to come and grab samples and then refill with clean bottles so that they can continue to run. In fact, it's running this morning, okay? And so this allows us to tap into the tile and to take samples as the tile flow. So we know basically what treatment that field, the water is flowing from, and so that's how we link what's lost to what treatment. So we also take pride in not micromanaging these plots, but actually treating this study just like a farm. And so we have farm-scale equipment. And so here you have a hay high boy that was retrofitted to drop cover crop seeds into a standing corn. And so just let me tell you, we were corn, soybeans. So this year was soybeans. Last year, 2015, we were corn. That's the data you're going to see. And the year before that, we were corn. And so we're going to proceed with a soybean, corn, soybean rotation. So we were able to drop seed, our cover crop seed, into this standing corn, and I can show you some pictures of what it looks like. This is December 4th, and you can see this is a good shot of the radish beginning to turn and desiccate, but the cereal rye is just getting started. And so, what happens is that when he comes in to strip till, he's strip tilled right between the rows, offset of the old corn stalks, and that's actually where the cover crops like to grow. And so he used his precision RTK guidance to come back in the spring and try to hit where that nitrogen was, also where the cover crop was. And you can see him I tried to get a picture of him lining that up to hit right where the residue of the cereal rye is currently after being terminated in the spring. And this is him checking. I have a very good collaborator, and he takes care of this system very well. So here's a shot. I know this table is busy, but I want you to focus on the first 4 rows. And so this is showing when I took the sample, the treatment that the sample came from, and this is a cover crop sample, how much nitrogen the cover crop took up at the time I took the sample, and then the biomass at the time I took the sample, okay? And so you can see in the first 4 rows, that's the first cover crop growing season, and in the fall, there was only a minimal amount of uptake, so 11 to 9 kilograms per hectare, and then the biomass was really low, almost 300 or so kilograms per hectare of biomass. But then if you fast forward to 2015 spring, you can see a drastic increase in the uptake, and most of that uptake is now coming from the cereal rye that's grown in the spring because the tillage radish has winter terminated. And you can see also a drastic increase in the biomass. The same thing occurred in 2015 and 16 growing season. However, that difference from the fall to the spring that you saw in 14 and 15 is not really there because it was so warm in this particular winter that there was a lot of growth in the fall, so you would not expect it to grow that much more in the spring. The growth kind of slows down. So takeaway points, over a 2-year period, on average, the cover crops absorbed or took up from the soil solution 25% of what was applied. So remember that rate was about 220 kilograms per hectare, which is about 200 pounds per acre. Okay, and so when you think about that mix, most people don't understand how the mix is operating. And what we found, so when we took the biomass sample, we separated out the cereal rye from the radish and found that the radish was accounting for about 55% of the biomass, although it terminated and didn't grow in both the spring and the fall and the spring. It still accounted for 55% of the biomass and 51% of the nitrogen uptake. Now, those of you that have dealt with radish before, you know that in the spring you can't tell that the radish is actually there because there's not a lot of residue on the ground. And so what that tells you is that 55% of what was taken up is probably already being released into an available inorganic form in the soil solution. Now, that could be a good thing and that could be a bad thing. If you're planting, let's say, soybeans and you come in late, but you have a lot of spring rainfall, then you're going to get a flush of that available nitrogen. Whereas if you have a cereal rye growing in the spring, that nitrogen is still assimilated into that residue, and that residue has a high C/N ratio, so the microbes take a long time to degrade it, so you have a slower release, less likely to lose it to denitrification, less likely to lose it to leaching. That's why it's good to have both. Now, if you were planting corn coming off of radish, it's great. It's kind of like a pop-up application of nitrogen that's being released from that radish, because remember, the radish has terminated, late December, January, and so it had a long time to decompose and to mineralize and to convert itself, that nitrogen from organic to inorganic where the plants could actually see it. So let's talk about how the cover crops impacted the tile water. So first of all, I know this is a busy graph. Let me just refresh your memory of the treatments. So we had spring nitrogen without cover crops, spring nitrogen with cover crops, fall nitrogen without, fall nitrogen with, and the zero control, no cover crop, no nitrogen. And you can see the associated symbols and colors that are listed. So the two green rectangles, the two green boxes that surround the dates are indicating to you when the cover crops were living, okay? And so on the two vertical axes, the one to your left is tile nitrate loss in pounds per acre, and the one to the right is rainfall in inches, okay? And that the gray bars are rainfall. And you can see that the rainfall really drives the actual loss of nitrate by tile, okay? So when we progress further, I've added when the nitrogen management occurred, and so you can see in November we had a fall application, and then we had the spring application sometime early June, okay? Then let's move forward and look at some of these events. So the March 12th event, where you see the first spike here in 2015, that's actually a snowmelt event. Now look at the difference in what was lost between the treatments. All of the treatments without cover crops lost greater nitrate through the tile during that snow melt event. So that's a protection that you get early spring when you have like a cereal right there that's actually living. If you do have that snow melt, you don't get the loss of the nitrogen that you would if you didn't have the cover crop there. If you fast forward to 2016, January 6th, another snow melt event that came after a big rainfall event, and look at the loss that occurred there from the treatments that did not have cover crops compared to the treatments that did, okay? We all remember the record high rainfall in June and you know, the rainfall that followed in July, and that's when we lost most of our nitrogen. And this is while the corn is growing, so the cover crops don't have a big effect on loss that occurs during the time when the corn is actually growing. But then after the cover crops are planted, somewhere around September 18th, you can start seeing that the green treatments, the treatments that have cover crops, have lower nitrate loss throughout all the way to April 21st, 2016, okay? So when we move forward, so this is a graph that's kind of showing you cumulative loss over the entire time that we monitored. So we monitored 32 flow events over a 19-month period, okay? And so each time, so this graph was made by each time that it rained, we added the current rainfall to the last rainfall to get a cumulative over time. So you're talking about somewhere close to 38 or so inches total over that 19-month period. And so, again, you see early on there's protection in the spring when you move from the fall of 2014 into the spring of 2015. That line is kind of flat. When the corn is growing, you get loss, and then that line goes flat again when the cover crops begin to grow in the fall of 15 going into the spring of 16. So the takeaway here is that, first of all, spring nitrogen, fall nitrogen, and the zero control lost on average 67 to 78 pounds per acre over that 19-month period. Okay? Now, someone's wondering how in the world does the plot or the treatment that has no nitrogen added and no cover crop would lose the same as a plot that have 200 units of nitrogen added? Well, first of all, the soils in McLean County and Central Illinois and in the Corn Belt, if you're taking care of the soils, you could have upwards to 3.5, 3.2% organic matter. So what you're going to get in the spring without even adding nitrogen is a plume of nitrogen release through natural mineralization of soil organic matter, okay, especially if you're in a tilled system, okay? So that's one source. And then this had only been a zero control for about 2 years, so there could be some residual still moving through that system. And when you have this, these two sources there, and you have, you're going to see the uptake of the corn and the yield of the corn. So not much nitrogen is being taken away from the soil solution compared to even when nitrogen added in a healthy corn plant growing rigorously that's taking up nitrogen at the correct rate. So you have a system that does not have a lot of demand on it. So a lot of that nitrogen is sitting in solution and then is actually moving through and reaching the tile at the same rate as the nitrogen left over that the corn didn't get when nitrogen was applied. Another takeaway. Fall nitrogen plus cover crop was equal to spring nitrogen plus cover crop when considering what was lost from the tile. So fall nitrogen plus cover crop lost about 46 pounds per acre, and spring nitrogen plus cover crop lost 45 pounds per acre. Those two were 40 to 42% less than spring without cover crop and spring control. So what that tells me is that there's potential that cover crops could have the same effect on fall nitrogen as it has had an effect on spring nitrogen. And we've seen numerous of studies, tile drainage studies, such as Pound Casper in Iowa with the USDA that have 14 years of data showing a decrease in nitrogen loss in a spring system when cover crops are added. And so here in this first year only, but one of the record high wet years, we see the same effect of cover crops on fall nitrogen as the spring nitrogen. So this is an interesting slide. So what I did was I basically tallied the nitrogen lost by the tile for each treatment when the corn was not growing, and I'm calling that the fall and spring fallow months, okay? Spring, and you can see the reduction. So 68% reduction when you add cover crops in tile nitrate loss in the fallow months when you add cover crops to a spring system, 68% reduction. For a fall system in the fallow months, that's a 58% reduction. So I did some further calculations and found that that's about the 49, or let's just say 50 pounds lost in the fallow months for the spring, and the 40, let's say 41 pounds per acre loss in the fallow months for the fall is about 60 to 63% of what's lost total over the 19 months. So you lost over half of the nitrogen when corn was not growing, when you did not have a cover crop, and only like 30 to 31% when you did have a cover crop there. So I thought that was pretty significant and something to consider when you think about the value of having a cover crop in your system. So let's go back and look at the cumulative graph, and we're going to look just at the 2015 corn season and the fallow period right behind it, where you have most of the loss from the residual. If you look down at this table, it says in-loss timing. This is the nitrogen loss. So across the top, you see the treatments, and then under in-loss timing is nitrogen loss during the growing season and then during the fallow months when the corn was not growing. You can see there again is reiterating what I just said previously on the previous slide, that spring nitrogen you lost almost the same during the growing season and in the fallow months when corn or cover crops were not there, which is a total of 67 pounds per acre. And then when you add cover crops, you drastically reduce what you lose in the fallow season, and that's but it's about the same loss during the growing season, but you come up with 41 pounds loss, and that same trend applies with the fall nitrogen. You lose about the same during the growth compared to when you don't have any corn growing, but if you add a cover crop, you drastically reduce what you lose in the fallow season. But even when you have a cover crop, you're losing about the same when the corn is growing. And then you see the zero control that lost basically the same amount of nitrogen as the spring and fall N applied. And that also tells us that we are losing a lot of nitrogen that's naturally mineralized from our soils. And even cover crops could capture some of that nitrogen. So here's the story right here. Okay, so far we've been talking about environmental measures. Now we're talking about agronomic measures. So 2015 corn in uptake and yield. And so across the top, you see V6, V12, VT, R6. Those are growth stages. V6 is where rapid uptake begins to occur. VT is the point at tasseling. Then R6 is relative maturity. And then you have the associated grain yields at the far right column, on the far right column. Okay, and so early on in V6, what we see is that the fall applied nitrogen, whether cover crops was there or not, was greater than relative to other treatments. Just note there that we hadn't side dressed yet. So basically the corn in the spring systems with and without cover crops were basically surviving off of what was residual, okay, from the previous corn crop. So as you progress from V12 to VT, you start seeing a decrease in nitrogen uptake where cover crops were involved compared to when cover crops were not involved. And my hypothesis there is that basically when you have the type of rainfall, the intensity of rainfall that we had during the growing season, cover crops locking some of that nitrogen up in its biomass could have reduced the total available nitrogen that was available for the corn crop after those flushes of rainfall went through the system. And so that equated into, for the spring system, it reduced so spring with cover crops had significantly lower yield compared to spring nitrogen without cover crops. I think we could have overcome that loss of nitrogen if we would have had some starter fertilizer applied with that corn in the spring plus cover crop treatment, something to get nitrogen into the corn early before those rainfalls, those large rainfall and high intensity rainfalls, storms occurred that flushed the system in the month of June and July. If that corn would have gotten some nitrogen in it early, I think it would have been okay. You would have seen comparable yields between spring in with and without cover crops. There was no difference in the yield when you added cover crops to the fall system. The yield was identical, but both the fall with cover crops and fall without were not significantly lower, but just lower in yield compared to spring. Now, let's focus on the zero control, which is the last row. When I saw that loss from my system, when I didn't add any nitrogen, the first thing that I said is that the other treatments are contaminating the zero control. That was one of the first things I wanted to determine. But when I look at the nitrogen uptake and how low it is for the zero control relative to other treatments, and then when I look at the associated yield for the zero control and how low it is compared to the other treatments, I can conclude that we're not getting contamination across treatment lines. We're just getting a lot of loss from what is possibly a small amount of residual nitrogen and a large percentage of nitrogen that's being mineralized. Now, we don't know that exactly, but that's the only nitrogen that was in that system, that was applied to that system. So what did we learn on the field scale? So first, about 53 pounds per acre on average, when you average across all treatments of nitrogen is absorbed or stabilized by the cover crop in the fallow periods. Now, what's neat is that that's 68% more than what was prevented from being lost through the tile. So there's a surplus of nitrogen there in the cover crop biomass, and we are actually conducting studies right now, litter bag studies and other types of studies, to figure out when is that nitrogen being released back to the next or the subsequent crop. Nitrogen application timing did not influence cover crop biomass or in uptake. In other words, the cover crop didn't grow better when you had spring nitrogen versus fall nitrogen. We didn't see that in this one-year study thus far. Okay. We may see it later, but we didn't see it yet. So during the corn growing season, we found that there was greater loss through the tile for the fall nitrogen system compared to the spring nitrogen system. And then during the fallow season, after harvest, we saw more loss from the spring system. So, for instance, when you saw that spike of rainfall in December, we all remember that it was warm and wet in December. We saw more loss from the spring system than the fall system during that time period. So when considering the entire 19 months where we monitored the tile, there was no difference between fall, spring nitrogen application systems and the zero control treatments. When you add cover crops to the fall nitrogen and spring nitrogen, you got a 40 to 42% reduction in what was leaving the tile as far as nitrate, despite the application timing. When you think about corn yield, we saw that spring nitrogen had the greatest corn yield, which was greater than fall, but fall without and with cover crops were equal, and those two were greater than spring with cover crops. So that leads me to the next scale, where we evaluated cover crops on a watershed scale. We wanted to see basically if we could transfer some of the benefits of cover crops environmentally, agronomically, to a watershed scale, okay? And so let's proceed into this study. So basically our objectives were to identify critical variables that influence cover crop growth, okay, on a watershed scale and nitrogen uptake, to determine the impact of watershed scale mass cover crop adoption. So we wanted to flood about 500 acres within one sub-watershed of the Lake Bloomington watershed to see if we can see an impact on water quality and impact on the soil inorganic nitrogen in the spring, which is very important. So here's a shot. We're in McLean County in the village of Towanda, and we found two watersheds. So the dark green is the treatment watershed, and the other is the controlled watershed. The controlled watershed is smaller, but similar soils in both watersheds. So the treatment watershed is about 1,100 acres, and the controlled watershed is about 770 acres. I think we were able to cover crops somewhere close to 48% of the larger watershed, which is, we're going to call that the treatment watershed. These two sub-watersheds contribute to Money Creek, which then contributes to Lake Bloomington, which then eventually contributes to the Illinois, which then contributes to the Mississippi River, Atchafalaya Basin, which then contributes to the Gulf of Mexico. So between the time frame of August 28th and September 9th, 2015, we cover crop approximately 528 acres or so, which is 48% of that treatment watershed. We did this aerially. Shirts Aerial helped us out there and dropped cover crop seeds into the watershed that was about 70% corn at the time and about 30% soybean. Here's just an aerial photograph taken by Shirts from his airplane on November 28th. You can kind of see the green in between the rows and also the green closer to the stream that converges where we were taking water samples. Here's another area photo. You can see the green really, the green from the cover crop really shows up well where we have residue from the soybeans, and that, in fact, we saw greater growth where you had soybeans compared to where you had corn stalks there, corn residue, simply because the soybeans, the residue is not as heavy. It allows for more light penetration, so you get more sunlight, you get more growth, compared to a system where cover crops were interseeded within standing corn. Here's a close-up look of all of the cover crop treatments within the watersheds. We did not dictate to the farmers what cover crops to choose. We allowed them to choose. They asked me questions, I gave advice, and then they made a decision, you know, and came back to me by email or by phone to tell me what cover crops they wanted to use on their acreage. And amazingly enough, we had about 5 to 6 farmers, and these farmers agreed upon the same exact thing in the watershed. I don't know how, maybe at the coffee shop, I don't know. But basically what they agreed to was before corn, we want to go radish oats. And before soybeans, we want to go cereal radish. So how this worked is that we paid for the cover crops to be planted, and also we paid for the cover crops to be terminated. We also found unanimously that all of the farmers decided not to allow me to commercially terminate, but they wanted to terminate themselves, and we compensated them for the termination, which is the same thing. So it worked They were involved. They took ownership, and I got a lot of comments about what was green. If you know where Towanda is, it's right off of I-55, and to have something green, 500 acres of green during the fall was something that grabbed people's attention. So the farmers got a lot of attention from the green that was grown in their fields. You can see the radish oats and soybeans, the top right-hand square. Those lines, a farmer decided to strip till or to inject his anhydrous into that radish oats, kind of like the practice that we developed the green application. So they called and say, hey, would it be okay to inject our anhydrous into the cover crop, the living cover crop? Will it mess it up? I said, no, go right ahead. We've studied this for 4 years, and it turned out pretty well. So we measured the biomass across that 528 acres by creating about 20-acre grids or so across the entire watershed. We had GPS points for each grid, and myself and a crew of students went out in the fall and the spring to take biomass sampling because we wanted to know how the cover crops were growing on a watershed scale, and where did we see high growth, low growth, and what was affecting the growth, because the growth is very important. So we took basically a 1 meter quadrant within these grids, and we pulled up we took the above ground biomass, took it back to the lab, dried it down, and measured it for percent nitrogen, and multiplication of the two would give you percent uptake by the cover crop on a dry weight basis. We also came back in the spring between the time period of April 18th and April 21st, right before planting, and took soil samples to a depth of 24 inches, and we divided that up into the first foot and second foot of soil. And we did that on a 10-acre grid. And we're looking forward to possibly getting a yield to kind of look at some correlations between cover crop growth, impact on spring soil nitrogen concentrations, and the impact on actually the actual corn and soybean yield in the watershed. So we took those samples and we measured inorganic nitrogen, which is nitrate, and ammonia. So I want you to get familiar with this picture because we're going to see a series of maps. And this is the as-applied application of the cover crops on the dates that I previously mentioned. And you can see the red is cereal radish, so it was dominated. About 80% of that watershed received cereal radish mix, and about 20% possibly received the daikon radish mix, okay? So you're going to see these shapes show up again. So here is the cover crop biomass production map. This is including both fall and spring biomass. You can see the shape, this green color, okay? That represents where the cereal radish mix was. This color is based upon the biomass, so I didn't make it green myself. The software gave it that color based upon a gradient of colors. You can see to your left from 0 to over 3,300 kilograms per hectare of biomass. Now, the outline in yellow is where the radish oats was applied. And you can see that we got greater biomass despite whether it was corn or soybean in the cereal plots overall when you consider growth from the fall to the spring. Then where you have radish oats, we had, pretty good biomass, but not as much consistently when you have cereal radish, the cereal radish mix. So if you look down to the bottom right-hand side of that screen, you see the two treatments on the left, and then you have cover crop biomass average. So the cereal radish mix averaged about 1,600 or so, 1,700 or so kilograms per hectare, whereas the daikon radish and oats mix averaged about 460 kilograms per hectare. So one interesting note is that so we measured the increase in biomass from the fall to the spring, and on average that was about 1,200 kilograms per hectare for the cereal rye. And that's why it's important to understand what cover crop you're choosing. So cereal rye grows both in the fall and in the spring, and the change in biomass between those two seasons was 1,200 or so kilograms per hectare. That's pretty significant. It's significant because you're getting the ground cover, so that's going to reduce erosion if you have any slope. And also, you're getting, the more biomass you have, the more nitrogen uptake you will have. But you have to consider what's coming after that cereal rye, so you can terminate on time. If you have corn, you want to terminate three or so weeks before, and then you want to add some starter fertilizer. If you have soybeans, you can let it go and then terminate about a week or two before you plant your soybean. So here's the associated cover crop nitrogen uptake from the biomass. And you can see for where you have the cereal rye, you had the greatest uptake compared to where you had the radish oats mix. The average uptake for the cereal rye radish mix was about 58 kilograms per hectare, which is very close to what we found on a field scale, so that's comparable, okay? Where you had radish oats, you got a lower average of about 21 kilograms per hectare. Now watch this, the change or the increase in uptake when you allow that cereal rye to keep growing from the fall to the spring was on average 42 kilograms per hectare. So that's a pretty big amount of nitrogen, large portion of nitrogen that the cover crops accumulated into the system and protected that nitrogen from leaching and from denitrification. So now this is very neat. We found that even on a watershed scale, different cover crops have a different impact on the spring available nitrogen. So this is the ammonium map that was from soils taken from a 0 to 12-inch depth. And you can see greater ammonium where the cereal rye was planted compared to the outline in yellow where the radish oats mixture was planted. And outside of what's outlined is we took soil samples from the places that did not have any cover crops, and we found that it was similar, more similar to the daikon radish and oats mixture compared to the cereal rye. Now this is a pretty significant trend that we're seeing here because remember, in the spring we want our nitrogen in the form of ammonium, which is a positively charged ion. Why? Because the soil is negatively charged, and so that ammonium will adsorb to the soil and not be lost compared to a nitrate, which is negative, and negative repels, right? And so when you get the rainfall, you get the movement of nitrate from the system. So basically, when you had where you had cereal rye, you had more of your nitrogen in the ammonium form. That's what we wanted. You can see the same trend exists at the second depth, the second foot depth. About you have more ammonium where you had cereal rye, and where you had the radish oats, it was similar to the places that did not have cover crops. All right, so when you think about soil nitrate at the first foot, it was the reverse. You had more soil nitrate where you had the radish oats compared to where you had cereal rye, and that's for the first foot. And then we see the same trend, but less of a trend for the second foot. So as we proceed to how the cover crops impacted the water quality, we noticed that the cover crops had a slight impact on reducing the discharge. So the graph to your right is the graph of the treatment watershed, and that gray box is where during the time period of where the cover crops were actually living. And we put that same box on the control watershed so you can know the time period, but cover crops were not there. At the top of each graph is the rainfall that occurred during the time period. So we saw, so in the control watershed, it's smaller and it normally has low flow. And so to see low flow, that's nothing abnormal. But in the treatment watershed, it's 1,100 acres surface area. So we're not used to seeing low flows. And so when we saw low flows in September and November, and then, going into early spring, we contributed that to be an impact of the actual cover crop, drying the soil out and using more water through transevaporation and allowing less discharge. So here's a shot of the impact of the cover crops on a watershed scale on nitrate. So that red line is the EPA drinking water standard, which is 10 ppm, and we see more points above that red line for the control watershed with no cover crops compared to less points above that line for the cover crop watershed. So that was pretty significant, and that's showing potential in the first year where we were able to reduce the concentration of nitrate in the tile below the EPA standard more often compared to when there were no cover crops on the controlled watershed. So what do we learn on a watershed scale? Mass adoption of cover crops on a watershed scale is possible. It may not work just this beautifully every year. I think this was a great year for cover crops because we had such high growing degree days, a warm and wet winter. The species or type of cover crop influences the type of soil inorganic nitrogen that you have. In the spring, we want ammonium rather than nitrate, and ammonium is also in the form where the crop can take it up. So that's very good. Nitrate is in that same form, but it's more likely to be lost through leaching. A cover crop that winter terminates results in greater nitrate in the soil in the spring compared to a cover crop that actually is winter hardy and grows in both fall and spring. It results in more soil ammonium. On a watershed scale, cover crops showed great potential in positively impacting the soil nitrate and reducing the load through the tile. So I'm going to say thank you at this point, and we'll address any questions that you may have, and my contact is also on this slide.
Great. Thank you so much, Dr. Armstrong. This is Julie back again, and we are able to take questions if you type them in there on the bottom right-hand corner of your screen. We can address any that you may have. And I don't know, we may have some in the room. Lauren, did you have any questions?
Dr. Armstrong, that was awesome.
Okay.
That is so much information, and I guess as I sit here representing farmers in the state, all across the state, who just pepper, us as an organization with a lot of questions on takeaways on practical, what worked best. And I know you worked very closely with the farmers on your fields, but as we're looking at, obviously the big picture is those cover crops really were effective at holding your nitrate, so it wasn't lost in the tile. So I take it back to the practical aspects of, who retrofitted that equipment, and how did you do that, and how does it work best to get those cover crops to get the stand that you need? So any kind of practical advice?
Yeah, so there's not much silage in our state, but if you do have corn silage, you could come behind corn silage and drill. Drilling has been the best result, but we know that in our state, because of our winters starting early, drilling late will impact your cover crop stand. So normally it's difficult to drill when you actually are taking the corn all the way to grain versus silage. So when you are trying to interseed, you want to fly it on, and that will allow you to drop the seed into standing corn during the time when you start seeing the canopy kind of dry down and you start seeing sunlight. You can walk through the canopy and kind of see the blotches of sunlight on the soil. And later when the corn starts to brown, that's when you can get pretty good sunlight to hit the surface and get a good stand, and it has to be timely. So in order to get the watershed cover crops, we flew that on, and we flew it on right before rainfalls. So you don't get the rainfall and you're flying it on, you can't take advantage. You can't take advantage of the soil moisture unless you drill. Okay.
Yep. Okay, we do have some questions. The first one is about CCA credits, and we have applied for those. I've got all the email addresses for those of you that registered, and so as soon as I have that information on how to apply for those credits, I will send that out to the group. Great question. And then we also have questions about the rates for the cover crops for the radish and rye. So I think the question, and Jeff, I know we can't hear you, but we saw your question. But the rates for the cover crops, radish and rye.
Yeah, so when we were applying these rates from the airplane aerially, our rates, I think, were about 80 to 90 pounds per acre. And that was suggested by Schertz Aerial because he was thinking that we needed more than what is normally required if you drill in order to get a good stand. Then if you are doing a ground-based rig that has been retrofitted, like a Hagee that has been retrofitted, and those are being retrofitted all across the Midwest, then you would slightly reduce the rate, but you still need a higher rate than if you would drill.
Okay. All right, Jeff, if that didn't get you, just type in again. We have another question about, and I'll just read it. So the wet spring and summer of 2016 seems to have had an impact on N loss last year. Do you have any information, predictions about how 2017 will turn out in terms of comparing fall applied in versus spring applied in with or without cover crops?
I cannot predict the weather. I wish I could. I would be rich, but I cannot predict the weather. But what I can say from my research and research of my colleagues and all that I've read, whenever you have above average rainfall and you compare fall versus spring nitrogen application, fall will lose that battle every time. If you have a winter where you actually have the ground to freeze, and you have average rainfall, and you're able to plant on time, normally, as far as loss, they will be equal. We did see that spring nitrogen application with abnormal rainfall in the fallow period after harvest resulted in greater loss, and I've seen that a couple different times. And so that's what I can say to that question. Okay,
and Laura, if you have follow-up to that, just go ahead and type that in. And then Scott has a question about the results from the first presentation. Mm-hmm. Regarding the results for about 205 per acre for both fall in application alone and fall in application plus cover crops. Does your research potential money savings? Basically, what do we see from an economics, the potential money savings?
Yeah. So basically, we are working on that because in that system, we can measure the nitrogen that is not lost through the tile based on cover crops being there. We also now have developed a method to measure the return of nitrogen from the cover crop residue over time. From the reading, we saw at least 50% of that nitrogen, the half-life of that nitrogen is about 30 to 40 days after termination, but we're going to verify that. And so also, I'm looking for a collaborator to help me with measuring the atmospheric component. So we would have three components that we could, that cover crops would impact that we could contribute towards a value of that cover crop. So we're trying to get to the point where we can basically quantify the amount of nitrogen in the cover crop and nitrogen that was saved or sequestered and how it converts to a yield to bring it back to the value of the cover crop.
Okay.
Awesome.
Okay. Let's see. Those were the questions that we had that were submitted from the group. And, you know, something I will add on the economic side is from Illinois NREC's perspective, that is definitely the next stage in a lot of the research that we're looking at is, you know, kind of as funding got ramped up and as our projects got going, we really needed to address just the practical, how do we get this to work on a farm? And now those are definitely the biggest questions that we're getting from producers, understandably, is what does this do to my economics? And we're kind of understanding from a production standpoint, from a water quality, and now that next piece is really addressing the economics.
Right. And so basically that's going to take being able to track nitrogen out of the cover crop biomass into the plant and then converting that to, and then determining how much of that has converted to yield.
Okay.
Right, and then from there we can back calculate, say, hey, you know, 50% of what was taken up, let's say 50 pounds was taken up, 25 pounds was actually used by that crop, so that crop actually got it from the soil and used it. And then based upon that, based on where you are with your application, we would know if that contributes to yield or not.
Okay.
Because if you're at a rate that's above where your yield stopped increasing, then we don't know if that's going to increase the yield or not.
Right. Great.
Can I have another question that just came in. So, you know, you talked a little bit about nitrification inhibitors.
Yes.
Okay. So can we talk a little bit more about the role that they've played either, you know, when you put it on in the spring with your nitrogen application, you know, what kind of effects were those having in the cover crop rotations as well?
Okay. So in my study, I did not evaluate the efficiency of the inhibitor. So I didn't have a treatment that says fall with inhibitor, fall without inhibitor. Everything had inhibitor.
Okay.
But what I can say, again, it goes back to the weather pattern. So from the plot scale study, in the year, I think the winter of 11 and 12, it was wet and warm. We had inhibitor applied at the correct rate, but we still saw the nitrogen that we injected move down to the lower depth. So what am I saying? In a year where you have the winter that we're used to, the inhibitor works very well, but it's limited in an environment where microbial activity is still rampant.
Okay.
It's just limited in the scope. When you think about 7 billion microbes in 1 teaspoon of soil, it's just limited. But when the microbial activity is reduced, and that's where that 50 degrees come from, so we say don't apply any fall applied nitrogen, when the soil is above 50, the temperature is above 50 degrees. That's because below 50 degrees, the activity of the microbes reduce drastically, and so you get less mineralization, so it's safer to apply. And that inhibitor works well below 50 degrees. But in those winters where it's, it could be 75 degrees outside and snow melting, it's just tough for that inhibitor to compete.
Okay. So this may be outside of the realm of this research project, but if we're talking about regular BMPs that we often recommend to farmers, are we still, would you still say that in those kind of winters the inhibitor is helpful with the fall applied or the spring applied?
Yeah.
It does its job?
It does its job under normal conditions. You get a winter like 11, 12, I'm not a meteorologist, but once, I would say, since I've been studying, once every 5 to 10 years, right? We kind of got one in 15, and you had one in 11, okay? But in the years in between where you have the normal environmental conditions by which the inhibitors is created to work under, it works.
Okay, great. Well, we are so grateful for you having spent the time to really find some solid answers on this really complicated issue for our producers in the state, and also for the retailers and all of the folks who give our farmers advice. So thank you very much, and thanks to all of you who joined us. Do we have any more questions?
Nope, that was it.
Okay. Well, thank you to everybody for spending your morning with us. Again, we have recorded all of this so that way we can all listen to it over and over again and memorize Dr. Armstrong's data. But again, thank you to everybody, and please join us again in August, where we'll have yet another researcher coming to talk about. And if you still have the slide up in front of you, all of Dr. Armstrong's contact information, his email, his phone number, are all up there on the screen, and so he welcomes your questions, and same to Julie as well. So thank you so much.